So a very quick review of what we have done in linear differential equations of second and higher orders. So a linear differential equation, when we have to solve, first of all, a linear differential equation is of this form: nth derivative of y plus n minus first derivative of y with a function of x, p, or a constant. So then p1, p2 times n minus second derivative of y plus pn times y is equal to x. This is the most general form of the linear differential equation of higher order, where p1, p2, p3, and pn are all functions of x alone. Now, a simplified version of this is linear differential equation with constant coefficients, which means all this p1, p2, p3 are constants. We replace them with k1, k2, k3, so up to kn, so on, because all are constants, and x is the only x on the right hand side is the function of x alone. It doesn't involve any y. So the solution is divided into two parts: solution of the homogeneous equation and solution of the non-homogeneous equation. Homogeneous equation means when x on the right hand side, x is 0, we get a homogeneous equation. If x is not equal to 0, we get a non-homogeneous equation. So for an nth order differential equation, you will have n solutions for the homogeneous component. So complete solution of nth order linear homogeneous differential equation will be of this form: c1y1 plus c2y2 plus so on up to cn yn, where cn c1 c2 c3 so on up to cn are arbitrary constants, and y1 y2 yn are functions which satisfy the homogeneous linear differential equation. So this is the general solution. This, for homogeneous differential equation, this is the general solution: c1 y1 plus c2 y2 so on up to cn yn, and this y1 to yn are linearly independent functions. That means one function cannot be written in terms of the other function. Now, particular solution for homogeneous equation means when for particular cases you are given boundary conditions, or conditions on x equal to, at x equal to 0, y is equal to 0, or with those conditions we find c1 to cn. So when we assign some specific values to these arbitrary constants, then it becomes a particular solution. Now, for a non-homogeneous equation, the general solution satisfies the equation, and the for a non-homogeneous equation, the solution of the homogeneous part also is the solution for the non-homogeneous part, because when you put u, it makes 0, but it is only a part of the solution. It is not the complete solution. So suppose U is the solution of the homogeneous part and V is a solution which satisfies this specific differential equation, linear differential equation as shown above, then U plus V will be the total solution. So this is the main concept of solving the linear differential equations with constant coefficients, and it is applicable for non-constant coefficients also. We will see that. So the total solution is U plus V. This is the solution of the non-homogeneous part of the differential equation. So U is called as the complementary function, V is called as the particular integral. So how to find these? We use the differential operators. How to find U and V? And the derivatives, the order of the derivatives is written in the form of d square d cube so on. The first d by dx is written as d square y by dx square written as d square so on. So because of this we get a polynomial in d. We write the linear differential equation like this. It forms a polynomial in d. F of d is equal to y is equal to f of d times y is equal to x. So this is a polynomial function of the differential operator d. Now this can be treated as an algebraic quantity. So based on this we found methods to find the complementary function. So this is a polynomial. Now to find the complementary function, that means solution for the homogeneous differential equation. So y cannot be 0, so this component has to be 0. So when we equate that to 0 and find the roots, we get cases where this function f of d equal to 0, we call it as the auxiliary equation. This has m roots, and now the cases are that when all roots are real and different, when all roots are real and different, and let's say there are n roots for the differential that auxiliary equation m1 m2 up to mn, then y is c1 times, so the functions are y1 is e power m1x, y2 is e power m2x, yn is e power mnx, and c1 c2 c3 are the arbitrary constants. So this is the general solution for the case when the auxiliary equation has all real and distinct roots. When two or more roots are real and equal, suppose two roots are real and equal, so instead of getting c1 e power m1x plus c2 e power m2x, we will get c1x plus c2 times e power m1x. That means root is m1 and m1, two repeated roots. We get this. If there are three repeated roots, so this will be the complementary solution. Two roots are repeated, all others are distinct. Suppose three roots are equal and all others are distinct. So here is an example of three roots equal. So m1 is repeating thrice and all others are distinct. Then we have this e power m1x is multiplied with c1x square plus c2x plus c3, and all others are simple functions, e power c4 e power m4x plus c5 e power m5x and so on. So, and suppose M1 and M2 are equal roots of one value, and M3, M4, M5 are equal roots of another value, then we get the coefficients like this. Because there are two roots repeated, we get C1x plus C2 e power k1x plus then C3 x square plus C4x plus C5 e power k2x plus C6 e power k6x and so on. So this is the case of repeated real roots. Now next is the case of complex roots. Alpha, suppose two roots are complex. Complex roots always occur in conjugate pairs if the coefficients are for coefficients of a polynomial equations are real, then complex roots occur in conjugate pairs. So if alpha plus I beta and alpha minus I beta are the roots, then this is the solution. E power alpha x times a cos beta x plus b sin beta x. So we can write this as e power alpha x c1 cos beta x plus c2 sin beta x. This will be if two roots are occurring in complex conjugate pairs. So they will contribute this portion to the complementary function. The rest others are the same if they are real roots. So for pair of complex roots, we get this. If two pairs of complex roots are equal, then we get like this: e power alpha x into c1x plus c2 cos beta x plus c3x plus c4 sin beta x, and remaining the same. So here lot of in linear differential equation part, these solutions, they are standard solutions, they have been derived, but we have to commit these to memory. We have to commit these to memory. So we did a number of examples on finding the finding for the homogeneous solution, finding the complementary function. So for homogeneous differential equation, finding the solution based on purely based on the above logic. We did a number of problems. We did a lot of practice on this. Now finding particular integral for a linear differential equation, this has, first of all, we need to understand this inverse operator f of d times y is equal to x will give how to find y is 1 by f of d times x. Now this and f of d is a differential operator, so 1 by f of d has to be an integral operator. So first of all, we have to find out two basic operations. Suppose what is 1 by d times x? So 1 by d times x is nothing but integral of x dx. So this 1 by d operator is integral of x. We showed this. What is then 1 by d minus a of x? That is e power ax into integral of x times e power minus ax. So this again we have to remember, this is a very, very important operator. So 1 by d is integral of x, 1 by d minus a times x is e power ax again into integral of x e power minus ax dx. So we showed this. Now once we know this, how to find particular integral? Now to find particular integral, it depends so much on what is our x, the right hand side. So the first case, when the right hand side is an exponential function. So I'll write a summary case here. We don't repeat the whole thing. When right hand side is an exponential function, excuse me, when right hand side has an exponential function, now this is f of d times y is equal to x, and x is e power ax. Suppose this d is replaced by a in the polynomial of d, and replacing a does not make that polynomial zero. That means a is not a root of the auxiliary equation. If a is not the root of the auxiliary equation, the particular integral is 1 by f of a times e power ax. If a is a root, but the a is not the root of the derivative of this auxiliary equation, so f dash a is not equal to 0, then particular integral is x upon first derivative f dash a times e power ax. If first two derivative, the function at a is 0 and the first derivative at a is 0, then and second derivative is not 0, then this is the particular integral. So we have to commit this to memory, and you cannot just blindly mug up. You have to do a number of problems associated with it. When you do that, we did a few problems, but you will have to practice that. Just a second. There's a problem. Just yeah. So particular integral with right hand side e power ax form. So we did a number of problems. Then suppose the right hand side is sine ax or sine of ax plus b or cos of ax plus b. Then interestingly, you have to make this integral into the f of d in terms of a perfect square, f of d square. We will show, and this is the solution for both for sine ax plus b and cos ax plus b. 1 by f of d square sine ax plus b is 1 by f of minus a square. D square is replaced by minus a square. So if f of minus a square is not equal to 0, again if f of minus a square is equal to 0 and its derivative is not equal to 0, then we get x upon f dash minus a square. And if the function and its first derivative are equal to 0 at minus a square, then go for the second derivative, and then this will be the particular integral x square upon f double dash minus a square sine ax plus b. So this has to be remembered, the case of finding particular integral. So we did a few problems here. Just hold on, it will load. Next, when x is of the form, right, when x is of the form x power m, then we just use the binomial expansion for binomial theorem, meaning whatever the 1 by f of d is there, we factorize it and then put an operator 1 by 1 plus d whole inverse, and then you convert that to the binomial polynomial of the binomial theorem using and for a negative or fractional index. When we use that, we get an expression and then apply the operator on this, and by applying the operator, and then finally we get a function, and then 1 by d is the integral of that function. This is how we use the particular integral. Another method is to use the partial fractions. That is the most general case. Then two difficult cases is when e power ax into bx. There's a tough case. This is the solution. 1 by f of d e power ax vx is take e power ax outside and 1 by f of d plus a times b. By this, you just have to operate on b, and whatever is b, we can deal with that, because b can be one of the above three functions, either e power ax or cos x or x power m. So then we can deal with this. So just this operation is needed. We did a few problems on this. And if x is any function, then we have to use the partial fractions, resolve into partial fractions, and like this, resolve it into partial fractions, and use that result 1 by d minus a of capital X is e power ax. E power ax, remember this is a, e power ax integral of capital X into e power minus ax. So using that, we solve and we find the particular integral. So these were what we have done so far. And so these are 5 cases which we have to remember and practice. Okay, we have done a number of problems from GATE questions. So you can go through the. Now we will do what if it is not a linear differential equation with constant coefficients. How to do? There are other methods. Let's do that. So we have two other methods to find particular integral. This one, very important one, is the method of variation of parameters. So the method of variation of parameters. So this method is applicable to equations of the form y double dash p of x times y dash plus q of x times y is equal to capital X. So this is a second order differential equation, linear differential equation, where these are not constants, they are functions of x. P is a function of x, q is a function of x, and right hand side is a function of x. Okay, now the method through variation of parameters is like this. First of all, let us say let y1 and y2 be the basis or the solution of the homogeneous part of the LDE. That is y double dash plus p of py dash plus qy is equal to 0. Okay. So this is the homogeneous part. So homogeneous part, the complementary function will have two solutions. Now let us say we find the solution y1 and y2. Then how to find the particular integral? We say that particular integral in this method of variation of parameters, we say, I will write the total complementary function. Then the complementary function is y is equal to c1 y1 plus c2 y2. Okay. The method of variation of parameters involves so what it says is that the particular integral says that the particular integral for the LDE, linear differential equation, is of the form let's say this we write as YP particular, this is YCF or YC complementary. So it is, instead of C1 and C2 as the arbitrary constants, we change that to functions of X. Ux Y1 plus Vx Y2. Okay. Now this I'll not go through the proofs of the steps, but what we do is we substitute in the differential equation, it should satisfy, and we use certain equations and we solve. What we get is we get u of x as minus of integral of y2 upon w times x, the right hand side of the differential equation. And what is this w? We'll just see. V is integral y1 by w times x dx. So where I'm skipping the proof completely. It's not necessary for us the proof. Now W is called as the Wronskian. W is equal to a determinant of y1, y2, y1 dash, y2 dash. Now this is called as the Wronskian. Just like we call as Jacobian of partial derivatives of various multivariate functions, like that, this is Wronskian. Now, so therefore the solution, therefore the particular integral is so y1 times u times y1. So we get minus integral y2 upon Wronskian times x dx times y1 plus integral y1 upon Wronskian times x dx times y2. This is the particular integral. This has to be remembered. This is applicable for all types of functions where p and q may be constant, so it may be linear differential equation with constant coefficient. Here, or it is valid for p and q being some other functions also. So this is a method of variation of parameters. So we take the complementary function, we change the parameters c1 and c2 into functions, and we find out those functions u and v such that this u times y1 plus v times y2 becomes the particular integral. So this is how we find u and v. So let us do an example. Now find the particular integral of d square y by dx square plus 4y equal to tan 2x. Now this is not in one of the standard forms anyway. All right, the right hand side, the standard forms e power x. So let's look at the solution. First of all, we have to find the complementary function. So finding the complementary function. So this is d square y plus 4y is equal to 0 for the homogeneous part. So from here we get d square plus 4 is 0. This is the auxiliary equation, which implies d is equal to plus or minus 2i. D is equal to plus or minus 2i. Okay. Now the complementary function y is equal to c1 e power alpha x. So e power alpha e power 0 times x times c1 cos beta alpha plus I beta plus or minus I beta. So the complementary function is e power alpha x c1 cos beta x plus c2 sin beta x. All right. So c1 times cos 2x plus c2 times sin 2x. This is the complementary function. Okay. Now using the method of variation of parameters, particular integral is minus integral of y2 upon Wronskian times x dx. This x is tan 2x, right? Times y1 is cos 2x plus integral y1 upon Wronskian times x dx sin 2x. So now how to find this Wronskian? So Wronskian W, this is integral of y1 y2, sorry, determinant of y1 y2 y1 dash y2 dash. So y1 is cos 2x, y2 is sin 2x. So cos 2x sin 2x, derivative of cos 2x is minus 2 sin 2x, and derivative of sin 2x is 2 cos 2x. This is 2 cos square 2x minus of minus becomes plus 2 sin square 2x. So the Wronskian is simply 2. 2 times cos square 2x plus sine square 2x. You will get 2. Okay. This is a Wronskian. So this was a simple equation. So now the first part. So integral minus integral. So u of x is this minus integral y2 upon Wronskian times x dx. So this is minus integral sine 2x upon 2. Y2 is sine 2x upon 2 and x is tan 2x. Okay, so sine 2x into tan 2x. Now we need to solve this particular equation. Okay, now this can be, we'll try to simplify this. This is sine upon cos. This is sine square 2x. Okay, we can do some variations of this. This is just a trick of solving the integral. Sine square can be written as 1 minus cos square 2x. This will be minus half times secant 2x minus cos 2x dx. Now these are standard integrals. We have converted to standard functions. So integral of secant x is log mod secant x plus tan x by the coefficient 2. And cos 2x integral is sine 2x upon 2. So this function u is minus 1 by 4 times log mod secant 2x plus tan 2x minus sine 2x. Now let us look at v. This is integral of y1 upon Wronskian times x dx. y1 is cos 2x. Wronskian value is 2. The function on the right hand side is tan 2x. This simply reduces to half sine 2x. An integral of sine 2x is minus cos 2x upon 2. So the solution now, therefore the particular integral u of x times y1 plus v of x times y2. So the particular integral is, now u is we just found. U is this 1 by 4 times. So minus 1 by 4 times log mod secant 2x plus tan 2x minus sin 2x. This is u, and what is y1? It is cos 2x plus v is 1 by 4 cos 2x times, okay, y2 is sin 2x. So this is the complementary function. So you get sine, oh, this is minus. So you get plus and minus cancels. We are left with minus 1 by 4 cos 2x log mod secant 2x plus tan 2x. So this is the particular integral. Okay, we'll do one or two more examples. Let us find the particular integral for the function for the LDE, linear differential equation, two upon 1 by e power x. Okay, so solution. So step one is to find complementary function. That means solution to d square minus 1 times y is equal to 0. Now, which means d square minus 1 equal to 0, which means d has two roots, minus 1 and plus 1. So therefore, the complementary function is c1 times e power minus x plus c2 times e power x. So this is the complementary function. Now, so this is our y1 and this is y2. Now, by the method of variation of parameters, the particular integral is u of x times y1 plus v of x times y2, where u of x is minus integral y2 upon Wronskian times capital X dx. So y1 is e power minus x, y2 is e power x. So we'll find that out. And so first of all, let us find the Wronskian. y1, y2, y1 dash, y2 dash determinant. So e power minus x, e power x. The first derivative is minus e power minus x. The second derivative is this. So we get 1 minus of minus 1. Again, we get 2. The Wronskian, we get 2. So now u of x is minus integral y2 upon Wronskian times x dx. So we get minus y2 is e power x, Wronskian is 2, and the right hand side of the linear differential equation is 2 by 1 plus e power x. 2 upon 1 plus e power x dx. So we get minus integral e power x by 1 plus e power x dx. The numerator is the derivative of the denominator. If we see differentiate the denominator, we get the numerator. So this is of the form integral f dash x upon f of x dx. The integral will be log mod x. So the integral is this. Of course, modulus of e power, modulus of 1 plus e power x. E power x is always positive. So 1 plus e power x is positive. So you can remove the modulus. We can differentiate this and see. Derivative of log is 1 upon 1 plus e power x times e power x. So you get this. So this is this is u of x. Next, v of x y1 is e power x by 2, and x is y1 is e power minus x 1. Okay, now this is e power minus x. Now this requires solving. So one thing we can do is divide by e power x. We get e power minus 2x by e power minus x plus 1 dx. So this is e power minus x into e power minus x by 1 plus e power minus x dx. Now substitute e power minus x as t. So minus e power minus x dx is equal to dt. So therefore this integral becomes, take one of them as t, and then this becomes minus dt by 1 plus t. So minus of 1 plus t minus 1 by 1 plus t, 1 minus 1 by 1 plus t dt. So we get minus of t minus log of 1 plus t. Replace t by e power minus x. So minus of e power minus x minus of minus plus log of 1 plus e power minus x. So this is v. Therefore, the particular integral what's it? U of x times y1 plus v of x times y2. Now, what is u of x? Log minus of log 1 plus e power x minus log of 1 plus e power x times e power minus x. V of x minus of e power minus x plus log of 1 plus e power minus x times y2, which is e power x. So multiply the first term, we can write just like this. The second term is minus 1 plus e power x. Of course, we can simplify this further. I'll simplify this as I'll simplify this further. This is log of e power x plus 1 by e power x. So so we get this as e power x times log of 1 plus e power x minus log of e power x. So log of e power x is x. Okay. So I simplify this. I get e power x minus e power minus x times log of 1 plus e power x. Then minus x e power x minus 1. This is your particular integral. All right, this is by using method of variation of parameters. We do like this. I'll stop here for today. In the next class, I will teach the method of undetermined coefficients and Euler-Cauchy equation. With this, Euler-Cauchy equation is an important equation. With this, we complete the differential equations of higher orders. Then we have to go for partial differential equations. So one more class on differential equations, maybe an hour and a half. Okay, because I missed a number of classes last 2 weeks. If seeing my schedule this week, if time permits, I will announce some classes during the weekdays for 1 hour after 7 sometime. So I'll share this right now. You should practice this methods. I will share this notes of this class.